My name is Jonah Pignon, and I'm the group leader of the project. I originally suggested that we study the chemical challenges of storing a sulfur pile near Galveston Bay. Okay, real quick, I'm going to go over a quick little table of contents. Going to be about a slide about us, then followed by one that's going to be talking about our thesis, one that's going to be talking about the chemical aspects of the thesis and the findings, and then followed by the mechanical aspects of the thesis, and then the findings after that. Then we're going to just do some final remarks, and then finally to show you guys our sources. Now, about the team, our name was the OGs, and we had 6 members. I was a team manager. Luke was the team facilitator. Andre was the manager, and then Marvel, Cole, and Jacob were all the research facilitators. Those are all of our jobs, respectively. Our team agreement was just to do the best in every assignment and to learn something from each other along the way. Our largest challenge was to meet together to make decisive decisions, really just because we all had very busy schedules. We saw this through virtual meetings, and our agreement is what kept us together and unified as a team to complete our goal. Now, real quick, this is just a quick thesis overview. Basically, what we're going to go over is just like how to effectively design a boat propeller considering like marine life efficiency and chemical resistance. Real quick, we're going to go into the chemical aspects and the mechanical aspects of how we would do that.
Okay, moving on from our thesis, we want to first address the main issues when designing a boat propeller. Design an effective boat propeller isn't just about the power and speed, it's about balancing efficiency, durability, and overall environmental friendly. First off is weight mitigation. We want to ensure we use lightweight materials as they mean less energy is needed, increasing fuel efficiency and overall reducing emissions. And this makes for a more eco-friendly and cost-effective design. Again, salt water is highly corrosive. As you can see in the SS Salma off the coast of Pelican Island, again, we want to apply protective coating to these propellers, acting as shield against corrosion, extending the lifespan, and overall reducing the maintenance costs. Again, in saltwater environments, abrasion from salt and sand is also a real issue. Abrasion-resistant materials would help these propellers withstand this wear, maintain their shape and performance over time. Again, to overall just move efficiently through water, a propeller must have the right shape and angle. So yeah, hydrodynamic design ensures both smooth water flow, which reduces drag and fuel consumption. Finally, we want to consider the environmental impacts. Propellers can disrupt marine wildlife, introduce toxins, and create noise pollution. So yeah, by using non-toxic materials and minimizing noise, we're designing propellers that are safer for our marine ecosystems.
Hello, my name is Jacob Black, and I am one of the research facilitators. Now, after discussing the primary problems, I'm here to talk about the chemical solutions to deal with issues such as corrosion and microorganism buildup. Now, based on our thesis, we want our boat propeller to have resistance to chemicals in the ocean that lead to degradation while keeping marine life in mind. To ensure that materials that withstand the ocean will continue to withstand said conditions, we must take some precautions. Chemical bactericides or antifoulants are a substance that is applied onto marine structures, such as boats, to prevent or reduce the buildup of marine microorganisms, or also known as biofouling. Antifoulants minimize the adhesion of organic materials to surfaces, stopping the buildup from corroding a marine structure. However, this option is less safe for marine ecosystems as these chemicals can be harmful to the natural environment and microorganisms can grow resistant to said chemicals over time. Another way to protect the marine structures from marine elements is putting a protective coating on top. Coatings such as polymeric coatings or nanomaterials can create a physical barrier between the corrosive marine elements and the surface on the marine structures. The bottom image displays this relationship between protective coatings and microorganism buildup. These coatings are able to minimize corrosion and biofouling while being safe for the marine environment. However, one downside is that these coatings have to be reapplied constantly. Finally, our eco-friendly chemical inhibitors. Eco-friendly chemical inhibitors are derived from natural compounds such as plant-based extracts, which makes them non-toxic to the marine environment while protecting the marine structures. These inhibitors are cost-effective, environmentally friendly to synthesize, and can be used to protect a variety of metals.
Hello, my name is Marvel, and I'm a research facilitator. Today, I'll quickly walk through some critical mechanical challenges in engineering. First is going to be resistance to aberration. Important for materials facing friction includes toughness, impact resistant, and hardness, resistance to wear and scratches, propeller stiffness, maintain shape under stress, essential for stable, high-speed applications. Three is high strength to weight ratio, needed for strong, lightweight materials, including tensile strength, resistance to breaking under tension. Weldability allows for easy joining of materials while keeping structural strength. These factors are all crucial in designing an efficient and durable component. Thank you.
Okay. Hi, my name is Andre Mejia. I'm the project manager, and I will talk to you about the typical alloys that we have found are used in propellers. For the sake of propeller manufacturing, typically stainless steel, bronze, aluminum, and nitrile are the main candidates, particularly due to a combination of high tensile strength and resistance to corrosion and general stiffness. In particularly, we have found that by reducing the weight, their greater efficiency could be achieved by and large by reducing the overall stress on the motor. To this extent, we have narrowed it down to three candidate materials being magnesium alloy, carbon fiber, and titanium alloy. Starting with magnesium alloy, it is far lighter than aluminum. It has very high strength to weight ratio, mostly comparable to even and or exceeding aluminum or even inching to or stainless steel. It's environmentally neutral. The manufacturing process is easy, and deficiencies such as low corrosion and even still wanting strength can be remedied by the introduction of certain doping agents or rather alloying agents such as calcium. However, it can be fairly difficult to weld. Then there's carbon fiber, which again, it is stronger than stainless steel twice, in fact, and can be stiff. However, it can be very brittle, and it's also very difficult to manufacture, which also would raise costs. Still, it is perhaps the lightest option out of the list. Then there's titanium alloy, again, for lighter than the prior candidates, has very high strength to weight, age corrosion resistance. It's very hard, high tensile strength. Still is the manufacture can be complex, and it also has very high cost. Now, moving on to another solution, it would be to alter the shape of the propellers, moving from traditional to a more novel toroidal propellers, which have been shown to be more efficient. They reduce cavitation, which also contributes to a reduction of noise. They're more compact, meaning that they need a lower diameter to generate comparable amount of thrust, as well as in general generate more thrust than their counterparts. However, they can induce more stress upon the motor or drive shaft, as well as being quite complex, which would need more novel manufacturing techniques such as additive manufacturing or specialized casts.
Hello, my name is Luke Smith, and I'm the team facilitator. In conclusion, in order to effectively design a boat propeller considering marine life, efficiency, and chemical resistance, we must research ways to overcome negative effects of chemical aspects when considering the propeller, such as beneficial coatings that could potentially harm the wildlife and environment. On the chemical side of the equation, minimizing the corrosion would be optimal, but anti-corrosion coatings could end up hurting the environment on a higher scale than the benefit of the substance. On the mechanical problems, the dimensions of the propeller itself are very important to optimize in order to maximize efficiency, such as energy consumed per meter traveled and revolutions per minute. The specific material can make a huge impact on the efficiency of the propeller as well, based on weight and malleability. If the material were too soft, it would end up degrading too fast, ultimately resulting in a net loss. And based on our assessment, magnesium alloy is the best material to use in these regards. And here are our sources. Thank you for your time.